Thank you, Fadel, for the introduction, and thank everybody for being here. I'm Zhihong. Today, I'm very excited to present you about my research work, 3D backscatter localization for fine-grained robotics. This is a joint work with my colleague Qiping, Yunfei, Manish, and Fadel from MIT Media Lab. Today, we're witnessing a trend of robots moving towards more fine-grained tasks. For example, in traditional factory, in the assembly line, there are usually a large number of robots dedicated for different tasks. They just pick up the same parts from the same place and execute the same task over and over again. However, there is a growing interest to replace this robot with few more autonomous and agile robots that can perform a variety of tasks according to what they have perceived. Two most important abilities to enable this is identification and localization. Let's take robot grasping as an example. First, you need to identify the object of interest. Then you need to locate it before you can approach it and do the grasping. Nowadays, almost all of the robotic systems rely on vision for identification and localization, and that has been showing some great progress. For example, here in the video, we can see a robotic system use vision will be able to identify the bin, locate where it is, and go ahead and pick up into the box. However, one thing to notice is that the environment they operate is pretty ideal. There's little or no clutter, everything is almost in line of sight, and everything is kind of known, which make the identification and localization much simpler. Unfortunately, the real environment is closer to this. It's usually much more clutter, and there's some object in the non-line of sight, and there may be some unseen object that is novel. So it makes the vision system much harder to identify and locate. In fact, in general, vision systems, they suffer in cluttered environment, they fail in non-line of sight, and they require extensive training for the identification. So we're wondering, is there any alternative that can augment or even replace vision system for identification and localization? In the past few years, we have seen a lot of research work in RFID localization. So we're asking this question: can we use RFID localization for fine-grained robotic tasks? The application scenario is pretty simple. We have an image like this, and we have an environment like this, and we have the RFID, which costs about 3 cents each. And we tag all the objects of interest with RFID. In fact, a lot of companies are trying to replace barcode with RFID, so many of the manufactured products already tagged with RFID. One of the biggest advantages of using RFID is that it contains the ID automatically, so identification is trivial. So about localization. Specifically, we're looking for two things. First, we want sub-centimeter scale precision. Imagine you want to do robot grasping, you want the gripper to approach to the object with a very fine granularity. So you need that level of accuracy. And second thing is that you want to be able to deal with motion. Think about two robot arms that cooperatively, they want to hand over certain objects, and the object is in motion. You want to be able to track it even though it's in option. So do we have the ability to do localization right now? Unfortunately, state-of-the-art RFID localization system, they either lack the accuracy or they don't have the ability to deal with motion. So in this talk, I'll be presenting to you the first RFID-based localization system that enable fine-grained robotic tasks. Let me first show you some of the tasks that we can deliver. Here, we use TurboTrack to be able to check a robotic handover. Essentially, there will be an object tagged with RFID, and one robot arm will pick it up and pass it to a second robot. And here I show the tracking outputs. This is a 3D coordinate system with X, Y, Z axis, and the blue color represents the ground truth, which is obtained by optical system, and red color represents the output of our system. As you can see, two trajectories are very close, and we have a very high level of accuracy. And second task we try to do is that we try to localize nanodrones like this by attaching them with RFID. And what we show is that we can enable multiple drones flying in the air in very difficult trajectory and still achieve a very high level of accuracy for both of them. So in this talk, I will be telling you how we managed to do this. I will introduce you to TurboTrack, the system that can localize backscatter nodes like RFID with very high accuracy, sub-centimeter in all three axes, ultra-low latency, 7.5 millisecond end-to-end latency, high frame rate of 300 Hertz. And then at the core of our technique is a super-resolution framework that can fuse spatial temporal measurement over time. And then we do the real-time implementation and deliver our tasks on multiple fine-grained robotic tasks. First, let me tell you from high level how TurboTrack can localize objects. The way you localize is by estimating distance. Let's say we have an RFID here, and we have an antenna here. Then according to the received signal antenna, let's say we'll somehow be able to estimate distance between them. then we know that the RFID is on the circle centered at the antenna with a radius of d1. Now, if we add one more antenna and two more antenna, we will find that we can simply estimate the distance as the intersection point of all three circles. Localize by estimating distance is a standard practice, and people usually do it differently in how they estimate distance. In general, there are two ways of estimating distance. The first way is by measuring the time of flight. The way it works is like this. You transmit a symbol at a certain time t, and then the signal will propagate in the air, reflected by the RFID, and get back to the receiver at some time t plus delta t. What we want to do is that use the signal we receive to estimate the delta t, the time difference, or here will be the time of flight of this trip. Then, because we know the speed of the signal we can simply map it to distance as distance equals to time of flight multiplied by the speed of light. However, because you process all the data in discrete sampling, there will have certain time resolution, which will translate to a distance resolution equal to time resolution multiplied by speed of light. What does this distance resolution means in localization? It means that instead of having the RFID on a circle, we can only know that the RFID is within a strip, which have a width proportional to the distance resolution. So the true problem here is what is the distance resolution we can have? Remember, distance resolution equals to time resolution multiplied by the speed of light. And for standard networking device like LTE or Wi-Fi, they have a time resolution of about 10 nanoseconds, which translates to a distance resolution of 3 meters. So if you use this for localization with one more antenna, you can see that instead of finding the intersection points, we can only know the RFID is within an intersection region. And because of the width of the strip is of the scale of meter, the region is pretty large with respect to the sub-centimeter accuracy we are looking for. So simply by measuring the time of flight, we can only achieve very poor localization accuracy. Then what are the second approach? The second approach people try to use is by measuring the phase of the signal. Let me explain what it means. First, the transmitter will transmit a signal. When a signal propagates in the air, it's like a wave, and the phase will change over time. Therefore, all you need to do at the receiver side is basically measure the phase you received. And then you can map the phase back to the distance by using the equation phi equals to 2 pi d over lambda, where phi is the received phase, d is the distance, and lambda is the wavelength. It seems trivial. Now that if you have a very accurate phase estimate, then you can directly map to a very precise distance estimation. However, the full equation has a modular 2 pi, which makes everything different. Because when you have a modular 2 pi, it means that for any d plus n lambda, where n is any integer, they'll have the same phase as d. What it means is that instead of knowing exactly the distance candidate, you can only know that the distance is within a range of candidates which are separated by integer times lambda. And the number of candidates is huge. What this means for localization is that instead of being on a circle, you can be on any circle whose radius is integer times lambda smaller or integer times lambda larger than the circles. And if you do this for localization, it means that instead of having only one intersection point, you have a huge number of the candidates that because of the phase cycle ambiguity, and you have no way to resolve this. So let me briefly review two of the methods I mentioned to you. Using time of flight measurement, there will be no ambiguity. However, the local accuracy is very low. Using the phase measurement, you will have very high precision for each candidate. However, it's pretty ambiguous because you have no idea which one of they are. So how are we going to do better than this? One simple idea is that why don't we just combine both of them? By using the time of flight measurement to eliminate most of the candidates and only keep those candidates that's within the strips. By doing this, we'll be able to maintain the same level of precision provided by the phase, but have a much less ambiguities. However, even with this, if you have two more antennas, you can still see there is still a significant number of candidates left. You still need to address which one of them is the correct one. One way of doing this is by adding one more antenna. Why? Let's say in noiseless case. What is great about this is that in noiseless case, all the three circles are going to perfectly intersect at the true location and only at the true location, which is great. It means that you just need to add one more antenna compute the intersection point, and you can estimate it as the position. However, in reality, there's noise. When there's noise, the distance estimate will be distorted. The circles may not intercept at all. Or maybe even worse, the circles may intersect at a wrong candidate, then you will completely throw yourself off. So are we doing here? Is there really no way for us to combine all these measurements across antennas? Actually, no. If we somehow be able to model the noise and all the knowledge we have, we should be able to fuse all the measurements across antennas. That's why I'm telling you our super-resolution algorithm that will be able to fuse spatial measurement using a Bayesian framework. Let me tell you what I mean by this. Let's go back to this case where we have multiple candidates in the strips. And let's go back to 1D. What I want to do is I want to model the distance distribution along this one direction. So we have all the candidates due to the phase measurement. So how are we going to model this with the x-axis distance and y-axis as probability? One way to do that is, of course, to model it as a discrete distribution. By doing this, you'll be able to leverage the information you have from the phase measurement. However, you completely ignore the fact that there will be noise. So as long as there's any noise in practice environment, you cannot find the intersection. What will be the second way? The second way is modeled as a Y-Gaussian, which is generally used for filtering. Y-Gaussian will cover the whole range of distance, therefore it will cover the noise. However, it's problematic because you didn't leverage the fact that because of phase measurement, you know there are certain distance candidates that have much higher likelihood than other distance. Our idea is instead modeled it as a mixture of narrow Gaussian. For the mixture of narrow Gaussian, the position of the Gaussians will be determined by the phase measurement. The weight of the Gaussian will be determined by the time of flight measurement. And the width or the variance of the Gaussian will be determined by the noise level. Therefore, by this model, we can very accurately capture all the information we know from phase and time of flight measurement, and we can generalize to practical scenario where noise exists. Let me show you an example of how this will work. Here, we have the actual 2D setup with one reader and one RFID. Here, I show you the output as a probability heat map with navy blue background and yellow indicating position with high likelihood. As you can see here, there is a sequence of concentric circles because of narrow mixture of Gaussian. And then if you combine the second antenna, the third antenna, you will see by the third antenna, the position with the highest likelihood already corresponds to the right candidate. It's very close to the true position. What does it mean is that, great, by doing model as a mixture of Gaussian, you will be able to converge to the right candidate. However, in another experiment, also with 3 antennas, what we observe is that the candidate corresponding to the highest likelihood is wrong, which means that even though fusing the measurement across antenna is good, it's still not sufficient to deliver what we want in all the scenarios. Therefore, we rethink about the problem. Instead of fusing the measurement only across space and antennas, we think about fuse the measurement across time as well. Or put it differently, we try to fuse the spatial temporal measurement. The idea is that we want to leverage the target motion and combine the measurement over time. The key point is that when the target moves in the environment, the noise is going to change. And then overall, if you can converge, if you can fuse all the measurement across time, the right trajectory will be the one that makes most sense. Let me show you what I mean by this. Here, in the first frame, the true location is different from the highest position. However, at the second frame, as you can see, it fuses the measurement from previous frame, and the position and the weight of the candidates change over time. Then if we keep doing this, as the target moves, you will update the weight, and then at the 7th frame, we'll be able to converge to the right candidate. And then after this, you will see that as the tag moves along its trajectory, we'll be able to get more and more confidence in the right positions. And when the motion ends, we'll be able to backtrace and recover the whole trajectory. Shown here, the red color is the estimated trajectory, and the green color is the true trajectory. As you can see, two trajectories almost overlap because we have a very high level of accuracy. So I just show you how space-time super-resolution work in an example. Let me show you how we model it. Of course, we need a mixture of Gaussian, where the n represents each Gaussian, and w and summation of the weights equals 1. And then we need to fuse them across space, essentially by taking the product of all the mixture of Gaussians across antennas. And we fuse them across temporally by define a Markov transition model where we define a normal variable representing the motion. Notice that the transition model here is linear. However, the spatial fusion, the observation model we have is nonlinear. This is problematic because the nonlinear observation model makes generating the probability heat maps or other method for linear model computationally expensive. To address this, we propose an approximate inference algorithm which is very computationally efficient with a complexity of big O of n, where n is the number of candidates. In the interest of time, I will not dive into detail about our approximate inference algorithm, but I will be happy to take any question after the talk. So now, great. We have a very efficient algorithm whose complexity is proportional to the number of candidates. Then the question to ask is, okay, so how many candidates do we have? Remember that number of candidates depends on the time resolution and the wavelength. Specifically, number of candidates equals to distance resolution over the wavelength. Wavelength is about 30 centimeters for 1 gigahertz. Distance resolution, as I mentioned to you, is about 3 meters for Wi-Fi or cellular device, which gives us about 10 candidates if you use standard Wi-Fi or LTE. However, the problem is standard RFID reader have 1,000 times worse time resolution than Wi-Fi or cellular device, which means that instead of 10 candidates, we have about 10,000 candidates, which will make the approximate algorithm very hard to convert. Our idea to address this is that we combine a standard RFID reader with a localization helper that has a much finer time resolution. The way it works is that you have RFID, instead of only responding to the reader, it responds also to a localization helper, which sample with a much finer time resolution or larger bandwidth. By doing this, essentially the localization will be able to reduce the number of candidates from every single packet, and then we later extend this idea on both links to enable backscatter-aware wideband estimation. To sum up, we have the localization helper that help you reduce the number of candidates, and we fit the measurement to the space-time super-resolution algorithm I just mentioned to you. That's why TurboTrack will be able to achieve such a high level of accuracy. Now that I already talked to you about our system design and our algorithm, let me tell you about our implementation. In our implementation, we implement our localization helper with standard software-defined radio USRP X310, and then we deliver a multi-threaded real-time processing module. For the RFID reader, we implemented on USRP N210 with the standard EPC Gen 2 protocol. For quantitative evaluation, we compare TurboTrack with two baselines. R5, which is the state-of-art system for localizing static objects, and RFI Draw, which is the state-of-art system for tracking a moving object using antenna array. And then our ground truth is OpticTrack, which is the optical motion capture system, and we evaluate our system in the fully furnished indoor environment with different kind of off-the-shelf RFIDs. And qualitatively, we use Roomba for 2D measurement and use robot arm and nanodrone for 3D evaluation. Next, let me show you some of our results. Here, I'm going to show you the 3D localization accuracy we have in line of sight situation. On the x-axis, we have the localization error in centimeter. On the y-axis, we have a fractional measurement. We conduct 5,000 experimental trials. Each of them lasts between 30 seconds and 1 minute. And the results show that we have a median error less than 0.8 centimeter across all axes, and 90 percentile error less than 2 centimeter across all axes. Even for challenging non-line of sight case, we can still deliver 90 percentile error less than 2 centimeter and median error less than 1 centimeter, which means that TurboTrack achieves sub-centimeter accuracy in all three directions with moving targets. Secondly, in order to show the importance of the space-time super-resolution, we compare TurboTrack to two partial implementations. The first one, we implement the same localization helper, but instead of mixture of narrow Gaussian, we fuse using a wide Gaussian. And the second one, we have a localization helper as well as an intersection-based method. We can see that with the localization helper, we can achieve a median error of about 17 centimeters. However, only with the space-time super-resolution, we'll be able to achieve the median error of 0.8 centimeter. This means that space-time super-resolution is very, very important to achieve the high level of accuracy. Next, I will plot the tracking error versus speed, where on the x-axis is the speed of centimeter per second in log scale. On the y-axis is the error in centimeter. As we can see here, the blue represent TurboTrack, and green and yellow represent the other two baselines. TurboTrack achieves much better accuracy across all the speeds. In fact, TurboTrack outperforms the state-of-the-art system by more than 100 times for standard speed in fine-grained robotic tasks. Also, I deliver some also nanodrones tasks other than the tasks I showed you in the beginning For example, we can track a drone docking to a table or a drone maneuvering in the air drawing a character N very accurately. For the robot arm, except for the handover I just told you, you also do packaging where you have two objects tagged with RFID and two robot arms cooperate with each other to finish the packaging operation. To conclude, TurboTrack localized backscatter nodes with sub-centimeter accuracy without any constraint on their location or their mobility. We introduced a new super-resolution framework that views spatial temporal measurement over time using a wideband localization helper. And we enable tracking for fine-grained robotic tasks like handover, packaging, and drone maneuvering. With that, I'm ready to wrap up my talk and answer any question you have. Thank you.
Hi, really interesting talk. Quick question, over what ranges are you detecting objects or tracking them?
This is a good question. I think we do our evaluation with passive, basically off-the-shelf RFIDs, which usually are working across 6 to 10 meters. But notice that this technique is very general to any backscatter node. So if your RFID is like battery assisted, it can work across 100 meters. So yeah, it's pretty general.
Cool, thanks.
Thanks, really interesting work. So I'm curious, for your super resolution algorithm, does it work for stationary objects as well, or do you require motion?
That's a good question as well. Basically, because we leverage the motion of the target in order to achieve such a high resolution. But one thing to notice is that even for robotic tasks, when the robot moves, even though the target didn't move, it creates difference in the environment, which essentially creates the same thing as motion of the target. So we can also do this. We didn't show it in here, but in our experiment, as long as our robot arm moves, the measurement will the noise will change over time, and which can also help us merge to the right correct location. So it doesn't really require it to be a static case. We can also work with that. Yes.
Cool. Thank you.
Thank you.
Ikalin from University of Michigan. In the very beginning of your talk, you mentioned environments with unknown objects, where that could be a challenge for vision-based robotic tasks. I wonder in your system, because I believe your system is tracking the locations of those RFID tags, right? Do you have to sort of accurately model those objects that you're operating with their shapes and other features regarding to the RFID tag?
I think basically what you try to ask is that because RFID essentially what we can get is a location information. We may need other information for some tasks like shape. But there is something we can, for example, if you want to estimate the pose of the object, you can just tag two RFID on the same object. Then you can roughly know the face. And also, as we say, we are looking for alternative to augment vision as well. So basically, vision will have much more richer content in these things, but we will have much more precise information about location. So maybe maybe there will be a way to merge these two kind of measurements together to use the benefit of both sides. Thank you.
Okay, thank you.
Okay, let's thank the speaker again.